Welcome to the lecture series on vitamins and nutrition. Today, as a continuation from the previous session, we are going to look into the different aspects of the mechanism of vitamin K, followed by little more details on vitamin K related physiologic changes that happens in our body, or rather we could say those impact that vitamin K can have on our physiology for the benefit of our overall metabolism, and those kind of deficiency conditions that might result when there is prolonged deprivation of vitamin K. We are also going to look at different aspects of, I would say, anti-vitamin K, or in other words you can also call it as antagonists for vitamin K. So we have already seen the chemistry of vitamin K in detail, and as I have told you earlier, vitamin K gets activated into a form, although the synthetic version of vitamin K is quite active, but the more active it is, the synthetic version can also be toxic. So that's one of the reason it's always good, especially for vitamin K and many of the vitamins for that matter, to obtain it from natural sources or from vegetables and the food sources whatever we take. Yeah, it is good. We do have supplements made when the demand for vitamins are more through synthetic methods, but there is nothing like you could always consider getting these vitamins from natural sources. So as we have been looking at the fat soluble nature of these vitamins, the vitamin A, D, E, K, there is a general, I would say, a pattern as far as the absorption is concerned. So these vitamins, if you look at most of them being fat soluble, we need a diet which is balanced with fat intake. At the same time, we also need to look at a diet where you have provision for these fat soluble vitamin to get absorbed. And one more prerequisite for all these fat soluble vitamins is the presence of bile salts, and being lipids in nature, they have to be emulsified efficiently to ensure good bioavailability across the gastrointestinal tract, especially when taken in the oral form. So that way vitamin K, being a fat soluble vitamin, would fit into all these criteria. So now we are going to look at different aspects. So we earlier looked at the side chain modification, dealkylation and alkylation of vitamin K, how it is getting metabolically active, and we also looked at the way how vitamin K redox cycling happens. Now we are going to look at little more into the aspect of how this metabolism would happen. Now I would like to show you one particular pathway, how vitamin is basically gets across in an efficient manner. Now in this we have to look into the structure of vitamin K, because vitamin K, as I have told you earlier, occurs in different versions, and I would say the structural activity relationship of vitamin K plays an important role. Look at this picture. So this is the concise metabolism of vitamin K. So the vitamin K from the dietary source is a quinone. So if you know quinone, the functional group is a ketone. So the quinone ring must be reduced into the quinol to become activated. In other words, there is what we call it like a precursor conversion. So the dietary quinone, so you see this is how it looks like. Now this is something like a kind of a ketoenol tautomerism. So here you see the ketone group gets converted into the phenolic group. So ketone getting converted to the phenolic group and vice versa. So when the ketone is reduced, you get the enol form, and when the phenolic form is oxidized, you get the ketone form. Now if you look at the structure of vitamin K, you know the vitamin K as a quinone ring. So this quinone ring gets converted into the phenol ring. This version of the hydroxy compound of minadione is the active form. So if you look at it, vitamin K, which is basically the quinone, gets activated to quinol and then again gets inactivated, and this is like a kind of a cycle. Now if you look at this, you do have, I would say, a series of enzymes playing a role. So here you have quinone reductase, an enzyme. So quinone reductase basically does this function of converting quinone into the enol form. Now you have carboxylase epoxidase. So carboxylase epoxidase is basically an enzyme that will use quinol as a cofactor to carry out gamma carboxylation of glutamic acid residue. So this is extremely essential. So glutamic acid is basically a side chain present in, I would say, the clotting factors, clotting proteins, the fibrin. So one example I can give you, if you could look at atta, the normal dough what we make it for bread and food sources. So if you carefully look at it, the flour contains, I would say, gluten and all the plant albumins, and they are rich in glutamic acid residues. Okay. Now the moment you add water, there is an enzyme called transglutaminase, and this particular enzyme will catalyze cross-linking of glutamine side chain with the amino side chains, and this glutamic acid amine side chain will form a amide linkage, and that's the transformation that happens. So with the moment you add water, the reaction starts in the presence of transglutaminase, and that's how you get that kind of a flexible dough what we make it for preparing bread. So the same mechanism also happens in the blood clotting. Now the fibrinogen gets converted to fibrin, and there the fibrin also has glutamic acid residues, and they cross link with the amine group, forming an amide linkage, and this kind of cross linking is what results in the blood clotting mechanism. And for that, the raw material would be, I would say, gamma carboxylated glutamic acid residues. So this gamma carboxylated glutamic acid residues are the key components in the clotting mechanism. And how do you obtain gamma carboxylation of glutamic acid residues? In the presence of carboxylase epoxidase, and this needs vitamin K as a cofactor. So hope you understand the mechanism, the metabolism. That's why we are so dependent on vitamin K for efficient clotting mechanism. So you could now by this time would have sensed any kind of vitamin K deficiency on a prolonged basis could definitely lead to hemorrhage related conditions. That's what we are going to see shortly. Now you see, the moment the cofactor vitamin K participates in this reaction, it becomes vitamin K23 epoxide. So this vitamin K23 epoxide is the inactive form of vitamin K, which is the quinol form of vitamin K. Because if you consider the quinone form, the quinone gets converted to quinol, and the quinol results in the vitamin K23 epoxide. Now if you consider, this is what I was telling you. So this particular enzyme, so vitamin K23 epoxide is the inactive form. So what exactly happens? That's oxidation of dihydroxy vitamin K to vitamin K23 epoxide. So this is the reaction I explained you right now. Now we are going to look at little more in detail. Whatever I have explained you, the same thing holds good. Now I will just show you or take you through those key statements so that you can pin this particular understanding in your mind. So you see, the production of 2,3 epoxide, or in other words we can also call vitamin K epoxide or vitamin K oxide, is catalyzed by vitamin K gamma glutamyl carboxylase. So this is the full name of this particular enzyme. So this particular enzyme is basically a quite big enzyme. I would say not very big, but relatively big, a 94 kilodalton protein, okay, and you find them in the organelles endoplasmic reticulum and in the Golgi apparatus, okay. So if you see this vitamin K23 epoxide, it's around 10% of the total vitamin K in the normal liver. In other words, what do you understand? Vitamin K being constantly, I would say, recycled. So if you could make a survey of how much amount of vitamin K, the active version and the derivatives and the metabolized version exist, we consider 10% of vitamin K epoxide would be there in the liver. Okay. Now this step is catalyzed by vitamin K epoxide reductase. So vitamin K epoxide can now be recycled back to vitamin K quinone. Now this is how the cycle goes. So in the liver and in the cells, this vitamin K epoxide, that's one of the reason why we don't so easily run out of the reserves of vitamin K, because the vitamin K which is being used in the reaction can be once again recycled. Maybe that's not the case for all vitamins, especially for water soluble vitamins, but for vitamin K it's almost self sufficient. So probably we need to just top up vitamin K regularly from a dietary source, and in most cases the top up what we do from the vegetable sources that we take is sufficient enough. So generally we don't run out of any kind of, I would say, deficiency disease for vitamin K, but if at all there is a deficiency disease for overall fat soluble vitamins, that's inclusive of vitamin K. Now you see there reductase dithiol dependent microsomal enzyme. Now very interesting thing to note, if you look at this particular compound, what we call it like coumarin type anticoagulants. I don't know you are familiar with this particular compound, this coumarin derivative. So coumarin is also a natural product, but the one which is very popular one used in therapy is basically warfarin. So all coumarin as anti-vitamin K mechanism of action. So what exactly they do? They go and inhibit this enzyme vitamin K epoxide. So this vitamin K epoxide reductase is inhibited by coumarin type of compounds like warfarin. Warfarin is a synthetic derivative of coumarin and a very popular one used for patients who suffer from minor clots or who have the problem of coronary artery diseases, and also patients who have problems with intermittent claudication. So any microclots that would travel here and there, okay, and could cause block of major capillaries and can give rise to problems, especially if the capillaries happens to be in the coronary network, it leads to coronary artery diseases. So as a maintenance dose, people are put on coumarin derivatives. I don't know you are aware of this or not. These coumarin derivatives are also used as rat poison. So most of the rat poisons available, if you just check the label, you will find them to be a coumarin derivative, potent coumarin derivative, more potent than warfarin. And in fact, when mice take this poison, they actually bleed to death. You know what happens in the rats or in the mice consuming this particular poison? It inhibits the metabolism of vitamin K recycling ability. So now you see how this particular vitamin K depletion, it's not that vitamin K is exactly depleted, you just seep into the pathway in which how vitamin K can be recycled. The moment this happens, vitamin K is not produced or recycled to the sufficient level, and this eventually affects blood clotting mechanism, and once blood clotting mechanism is affected, there starts this cycle of hemorrhage, internal hemorrhage, microclots, and it goes to, I would say, prolonged bleeding, and the animal will die. Okay, so now you might wonder, that's one of the reasons this coumarin derivatives, especially warfarin, has a very narrow therapeutic index. So you see a narrow therapeutic index. So you can ask a question, suppose if this particular enzyme is inhibited, and suppose if you take sufficient amount of vitamin K, would not the effects of warfarin be reversed? It's true. The effects of warfarin can be overridden by taking intravenous vitamin K, and that's what exactly people do, especially when warfarin toxicity results because of drug interaction or maybe overdosage or maybe deliberate accidents, whatever. You can actually supplement or override vitamin K hazard by taking intravenous or intramuscular sources of vitamin K. So you see, in addition to that, genetic variability in the vitamin K epoxide reductase is thought to account for the variability observed among patients in the response to warfarin therapy. This is again a very interesting note. Since I have explained you about what is warfarin, I think you may not seem puzzled when you look at this word warfarin. So you see, so when you put a patient on warfarin therapy, and you should be also well aware of the genetic components involved. So this area is one more specialty, what we call it as pharmacogenomics, influence of genetic variability. So why we have to study about this right now? Because we are dealing with vitamin K, and vitamin K mechanism and metabolism is closely associated in the way how our body would make use of vitamin K for coagulation mechanisms. And since warfarin directly interfere with vitamin K mechanism, any kind of genetic variability, I mean inherent variability in the epoxide reductase, vitamin K epoxide reductase, can have a major impact on the outcome of warfarin therapy. So probably these patients would be highly susceptible to warfarin therapy. Now if you look at it, what exactly happens? Now the final reductive step can be catalyzed in two ways. So vitamin K quinine reductase, it's a dithiol dependent microsomal enzyme and is inhibited by coumarin type anticoagulants. Again, one more thing, these coumarin derivatives are said to have a little broad spectrum activity. As we have seen, they are not only fond of epoxide reductase, but they are also fond of quinine reductase. So this is one more step. And again you have one more enzyme, what we call it like DT diopharase. This is also a microsomal flavoprotein that uses NADPH as a source of reducing equivalence. So if you recollect, vitamin K gets converted into the quinol form, and the quinol form, when catalyzes the carboxylase reaction, ends up being an epoxide form. Now the epoxide has to be converted into an oxide form, and that's the step of, I would say, reductase, quinine reductase, followed by that DT diopharase would ensure complete conversion of this particular enzyme. So this enzyme, I would say epoxide reductase, is a dithiol dependent microsomal enzyme. So this particular enzyme needs other two enzymes, vitamin K quinine reductase and DT diopharase, to complete the reaction. Now you see over there minoquinone. So what is minoquinone? It's the synthetic version of vitamin K. So this is rapidly metabolized and excreted, and you have, what do you say, a relatively minor or very little amount converted to MK4. Okay. So you see there, if you consider the primary route of distribution or elimination as you call it, it's like 70% of the physiological dose could be completely lost by renal excretion, okay, as a phosphate, sulfate or glucuronide or menadiol. So it means what? The vitamin K what we take would be converted into the thiol form and be utilized in the reactions, and rest would be released by conjugation reactions in the liver. So the liver is basically the organ of conjugation, and they bind with certain water soluble material, and the conjugate of vitamin K is more hydrophilic than the original compound. So that enables or would ensure then to be efficiently excreted by kidneys. So you see that they are also excreted in the bile as a glucuronide conjugate product. So you see that the minoquinone, what we have seen as a synthetic version of vitamin K, undergoes lots of conversions. Okay. So you see its catabolism appears to be much slower than that of menadione. Okay. So you see that the minoquinone derivative, so you have the total body pool of phylloquinone, about 100 milligrams in an adult, appears to have a turnaround in about 1.5 days. So this is the kind of metabolic kind of, I would say, the flow that you could expect for vitamin K, so that there is this reservoir of vitamin K being kind of replenished and used through this set of enzymes present in the pathway. Okay. So you see that you have a side chain activation happening, and whenever you add a side chain to it, okay, so that would delay the process, and the metabolites are given more scope to perform a reaction, so that they can actually replenish the reservoir source in the cytoplasm of the liver. Okay. So the primary route of, I would say, these metabolites, see if you look at these metabolites, they are fat soluble. because they do have a long chain attached to it, making it little more hydrophobic. So any compound which is more hydrophobic, it's more efficient that you would emulsify them in a bile and then excrete it. So here we are talking about vitamin K antagonists. I think I elaborated on this and I told you about how these anticoagulants, what we call them as warfarin derivatives or coumarin derivatives, how they exhibit their mechanism of action. Okay. Now you have to look at the attendant loss of dihydroquinone results in the loss of protein gamma carboxylation and consequently the loss of active GLA protein. So GLA protein is basically the gamma carboxylated glutamic acid derivative. So when they are tinkered, that particular area, you call them like GLA proteins. We are going to look at them. So that way it's a cofactor, and here you find the gamma carboxylation of peptide bound glutamic acid residues. So you see, this is a feature not only in the clotting mechanism, but you do have other physiological mechanism that follows a similar pathway wherever cross linking is required. Maybe you can also consider when you look at the surface proteins, especially remodeling of epidermal layers will also involve gamma carboxylation, and especially if you look at, I would say, nematodes or surface of nematodes, or I would say the cuticular layer, there again this kind of a reaction is likely to happen. Even in such cases, vitamin K kind of cofactors would be very essential in maintaining this cross-linked layer. Our scope is probably more on the clotting mechanism, but you do have other mechanisms in your body which would utilize this gamma carboxylation related conditions, but you also have other extensive applications of this gamma carboxylation reactions happening in wide variety of species. So you see there, this is coupled to the cleavage of CH bond and the formation of a carbon ion at the gamma position of a peptide bound glutamyl residue followed by carboxylation. So this is the intermediate reaction, how the reaction basically proceeds. So you see there, you have this kind of change. How do you technically call it? So we could consider this to be a kind of post-translational modification. So what is post-translational modification? So an mRNA is going to give rise to protein, but when you look into the final protein, which is functional in nature, there are lots of changes to its side chain that would ensure, or would, I would say, make it productive as a functional enzyme or a protein. So this kind of features are basically what we call it like the post-translational modification. Probably I can give you an analogy. If you buy a vehicle, normally the price is quoted as devoid of all accessories, and then you buy the vehicle. The moment you take the vehicle as being supplied by the company, it's not, although it is roadworthy to drive, you may not really, I would say, work on it. You have to add all these extra fittings to make the vehicle functional. So similarly, here you find the actual, I would say, protein may not be in the workable format, and you have to add this extra post-translated features like the features what we are talking about, the gamma carboxylation reactions, to make this category of proteins more functional. So there are several post-translational modifications happening in the protein, in the cytoplasm, to make it more, I would say, efficient, or rather saying efficient, even functional for that very matter. And this is one such type of post-translational modification. So you see over there the prothrombin, all 10 glutamyl residues in the position 7 to 33, but none of the remaining 33 glutamyl residues are gamma carboxylated. You see where this gamma carboxylation happens, especially in the clotting mechanism, prothrombin, because prothrombin, in that the 10 glutamyl residues in the position 7 to 33 are the key target sites for gamma carboxylation, and when this happens, then the prothrombin gets activated into thrombin. Now if you look at this picture, so this is the picture what I would say. Earlier we saw the picture of, I would say, vitamin K getting activated. Now we see vitamin K in action in a very close format. So you see over there the prothrombin precursor where you have a glutamic acid residue happening over there. Okay, so here you have the prothrombin, and now you have the vitamin K getting converted into the reduced form, and this will now result in the epoxide form. So you see that in the epoxide form, the epoxide ring moiety is over here, whereas here if you carefully notice, you have a gamma carboxylic acid. So you see that the gamma carboxylic acid, so you see one extra COOH group added over here. So this is what we mean by, I would say, carboxylation reactions, gamma carboxylation reactions. So this kind of changes would ensure the prothrombin to have efficient to efficiently participate in the cross-linking mechanism. Now, so this is what we consider as the glue protein. This is a representation of the earlier picture, but in a little more, I would say, elaborate form. So you see there the gamma carboxyl derivatives. Okay, by the way, how do you call this as gamma? So the functional group that's immediately attached to the carboxyl group is called the alpha, and as you go away from it, you designate the number alpha, beta, gamma, okay, delta, and so on. So you see there, so this kind of a gamma carboxylation, so you see several coagulation enzymes and other clotting proteins require addition of a second carboxylate. So once you have this carboxylate group added, that makes it possible for the compound, I would say the amino acid in this case, to quickly form an amide linkage. So the earlier examples I gave you, I elaborated on what is the necessity of this amide linkage in the cross-linking mechanism, and now I show you how gamma carboxylation is likely to happen regularly on all the clotting proteins. Okay, so you see there carboxylase, epoxidase carboxylates glutamic acid residues using vitamin K as a coenzyme to carry out this reaction. So you see the extra carboxyl group. You might ask how this carboxyl group can be useful. Now, especially for prothrombin, if you are going to look in the aspect of prothrombin, and carboxyl group has one pair of electron. Okay, so it's basically a nucleophile, as you see over here, and this acts like a kind of a chelating ligand, donating the lone pair of electron. So this kind of an arrangement provides a hook, or I would say the dentate, for binding with the calcium. In other words, technically we call it chelation of calcium. The moment the chelation of calcium happens, the entire cascade gets activated. So previously I told you this gamma carboxylation enables cross-linking mechanism. That's true, but for prothrombin you have an extra bit of function to add. The gamma carboxylation is the key for chelation. So this chelation, binding with calcium so that these proteins may adhere to membranes. So you see that a little tinkering of adding a gamma carboxylation tremendously changes the functionality of the protein, and now it becomes a kind of a chelating ligand with calcium to hold, and this creates a kind of an anchor for the protein to hang on. So I would like to wind up today's session, and I will quickly summarize. So we started with vitamin K, little bit reviewing on the mechanism. I told you the functional form of vitamin K because this is very essential. You might wonder, we have already seen vitamin A, D, E, K little elaborately, and vitamin K, although does not have much deficiency conditions, why we have to deal elaborately, because vitamin K is such an interesting compound, and you have a pool of vitamin K recycling happening, and that is the very reason that why we don't need too much of dietary supplements of vitamin K. But if at all this pool of vitamin K is disturbed, what all different kinds of complications that can result. So moreover, we saw exactly the role of vitamin K, how it does the gamma carboxylation and all the related enzymes, and also we saw the antagonist for vitamin K. So thank you for your participation and attention.